Rather than put you through the entire calculation for the de Broglie wavelength for an electron, I wanted to show you the important outcome that comes from that calculation. So I'm going to show you how big the electron is at two different velocities. We're going to focus on 1/10 of the speed of light, but I'll also show you the size of the electron at the speed of light, and we'll compare that to the size of an atom. Now, if we were to take the problem like this, we'd say, okay, what's the wavelength for electrons moving at 1/10 the speed of light? The speed of light's right here, so we'd take 1/10 of that. I've got the mass of the electron, and I've already converted it to kilograms, because Planck's constant, when you look it up in this form, is going to be 6.626 times 10 to the negative 34 kilograms. So by converting to kilograms, it will cross-cancel. I have meters times meters per second. So meter per second, that's going to be the velocity that I've got right here for speed of light. If I rearrange everything and I solve for that length in meters, I would get, at 1/10 the speed of light, 2.42 times 10 to the negative 11 meters. Now that's great, but when we have these small conversion factors and small exponents, it's hard to make sense of it, so let's go ahead and fix the metric prefix. If I convert that into picometers, then I'll be at 24.2 picometers. Now, 1/10 of a nanometer is going to be the size of many of these atoms. In other words, about 100 picometers, somewhere in that range, is going to be the size of an atom. So if we're at 1/10 of the speed of light, we're at about 2% of the size of the atom. And if we're at the speed of light, we're at a smaller size, but still something on the scale of the atom. In other words, if we have hydrogen, and our first radius is right about here, what we're finding out is this electron is not this tiny little particle here like we've thought at all. I know that in my analogy I like to say that this is kind of like the marble in the center of a football field, while the electron is a fruit fly zipping around at close to the speed of light, which was a reasonable way to think of it in terms of the masses. But when we actually get to what's going on with de Broglie wavelength, we're finding out that because it's a really light object moving really fast, it's going to be spread out in space. So the electron is actually going to be taking up about the space of half our first Bohr radius, half of n equals 1. Remember, radius is center out. So it's going to be half of the width of the atom. Okay, so our radius, it's going to be about half of that radius. Now, that means that electron is not that small little spot at all. It is actually spread out as a wave in space. So we can't know its position exactly, because it doesn't really have an exact position. The electron is actually this blob. It's been blurred out. It's been spread out like jelly on toast. So that's what we're talking about for the de Broglie wavelength of the electron.